Welcome to the final video of Chapter 6. And this is Section 6.8, and we're dealing with exponential growth and exponential decay. And there are about three main topics that are going to be required, but they present themselves in different ways. So here we go. Example number 1. We have the formula A equals 26 e to the kt power, and we're interested in the fact that t is the number of years after 1985, and we have 26 million in 1985, and 1997 it was 35 million, and so we get the exponential growth factor would look like this. And so we need to ask ourselves, find k to 3 decimal places. Okay, so what we do is our new value, we end up with 35 because it becomes 35 million. It was at 26 million, e to the kt, and that was in how many years? 12 years. So it's 12k, and our goal here is to find what does k equal rounded to 3 decimal places. So all we have to do is divide both sides by 26. So it's e to the 12k equals 35 over 26. And then to get rid of this e, we take the natural log of both sides. So we take the natural log of this side, and we'll get 12k. And we have to take the natural log of 35 over 26. And then divide both sides by 12. So that final answer will be the natural log of 35/26 over 12, which equals approximately 0.025. And realize this formula right here is an exponential growth model, where this represents the beginning value, in this case 26 million. This is the ending value. E is the number e. K is some constant that is determined by the type of problem. And then t, like always, represents the number of years. So, example number 2. Example number 2, we get, we're told this is the function. The number of books is 6,000. E raised to the 0.02t. And t is measured in years. How many books will the library have after 10 years? So that's relatively simple. Just plug in 10 in for t, so that's e to the 0.2, and 6,000 times e to the 0.2 would be 7,328 books. Example number 3. There are currently 73 million, so that means this number right here will be 73. And it's increasing exponentially at 5.9%. And when will this country have 81 million cars? So if we keep everything in terms of millions, we know we're going to need 81 million. We started out at 73 million. And that's e raised to the 0.059, because it's going by 5.9%, times t. Divide both sides by 73. E to the 0.059t equals 81/73. Take the natural log of both sides, and we get 0.059t equals the natural log of 81/73. And then divide both sides by 0.059, And this equals approximately, and I believe we're told round to the nearest year, that would be in 2 years. Example 4. The half-life of plutonium-234 is 9 hours. And if we start out at 60 milligrams, how much will be present in 2 days? Okay, so we need to do some calculating here. We're asking how much is going to be left. We start out with 60 milligrams. And half-life means we're losing 0.5 of it every time. 0.5, and then how long are we going to do it? Well, every 9 hours is the half-life. And in 2 days, we're going to have 48 hours. So that means we're going to go through 48 over 9 time periods. Or the fact that since it's 9 hours, every 9 hours we're losing half, we're going to go through 48 ninths of those sections or those time periods. And so it's just a matter of plugging all this in, 60 times e raised to the negative 0.5 times 48 ninths, and I believe that equals 4.169. That would be 4.169 milligrams is what would be left after 2 days. Example number 5. Realize these decay and growth problems aren't really difficult. It's just deciphering where does what go. And so once you've got that conquered, this becomes relatively simple. Number 5. Okay, we have only 900 fish left. Back several years ago, we had 1,600 of them. Specifically, we had 8 years ago. So that's k times 8, or raised to the 8k. And what we are trying to do is find out how rapidly are they dying off. That's the k, or the rate. So the first thing we have to do is to solve for k here. So we will divide both sides by 1,600. So e to the 8k equals 9/16 once we simplify. And then take the natural log of both sides, so that 8k equals the natural log of 9/16. Then divide both sides by 8, so that k equals the natural log of 9/16 divided by 8, which equals approximately, what, negative 0.072. So it appears to be losing ground 7.2% a year. But then we ask, when it gets to 100, then it's irreversible. They're going to be gone. And so we ask, when will this happen? So now we are asking, when will it become 100? And right now we are at 900, e to the negative 0.072 t. So we need to continue solving this. We divide both sides by 900. So e to the negative 0.072 t equals 1/9. Take the natural log of both sides. Negative 0.072 t is equal to the natural log of 1/9. And then divide both sides by negative 0.072. So the natural log of 1/9 over negative 0.072 is equal to approximately 31 years. So it's still going to be a while, but you know what? In 31 years, those fish would become extinct. Example number 6. Number 6, it has 60% of the carbon-14. And we know that carbon-14 decays at a rate of 0.0125% annually. So that means that's our ending, or that is the rate that we're doing. We're left with 60% of what we started out with. So we have 0.6 of what we started out with. The initial, we're going to assume 1, and 60% would give us the 0.6, equals E raised to the 0.000125t. Take the natural log of both sides, so 0.000125t equals the natural log of 0.6, and divide both sides by 0.000125. So we get the natural log of 0.6 divided by 0.000125, which equals approximately 4,087 years. And it is very similar. This is your carbon dating problem. So if you hear, oh yeah, we determined that this is 4,000 years old. Well, here's an example of it. It had 60% of the carbon-14 that it originally had, or should have had. And so that becomes the answer. Example number 7. So once again, realize none of these problems are majorly different than what we have. It's just a matter of setting them up. Okay. We're actually given a function, so those are pretty nice. 2700 e to the negative 0.02t. And t is measured in years. How many acres will the landfill have after 5 years? So that's just a matter of putting in a 5 right there. So 2700 times e raised to the negative 0.02 times 5, that's negative 0.1. So 2700 e raised to the negative 0.1 ends up being approximately 2,443 acres. Example number 8. Okay. We have to assume that it follows Newton's law of cooling, which is shown there, U equals T, all that business. And it's just a matter of knowing what each of those means. Okay. So U represents the final reading of the thermometer. So that would be 73. T represents the room temperature, and the room temperature is 37, plus U sub 0 is the beginning temperature, so that's 79, minus T, well T is still the room temperature, minus 37, e to the kt, and T is 13 minutes, so as long as we remember that we're dealing with minutes, we're good to keep it right there. And so now we are asked how long before it reaches the value we need here. Okay, so what we're going to do is, first thing we have to do is to find K here. So we will, let's see, subtract 37 first off, and let's see, let's rewrite this. 37 plus, this would be 42 e to the 13k. Subtract 37 from both sides, so we get that 36. 36 equals 42 e to the 13k. Divide both sides by 42, so that e to the 13k power equals, let's see, 42 over 36 reduces to, or 36 over 42 reduces to 6/7. Take the natural log of both sides, and divide both sides by 13. And so K will equal approximately negative 0.012. Now what we have to do is determine when will the final temperature be 57. So we've found what K is, negative 0.012. And so now we have to put it into the Newton's law of cooling once again. We want to know when will it be 57 degrees when the room temperature is still 37. It started out at 73, or that's where it is right at the moment, and minus the room temperature of 37, e to the negative 0.012 t. And we need to find out how much time will this be. Okay, so rewriting this, 57 equals 37 plus, let's see, that is 36 e to the negative 0.012 t. Subtract 37 from both sides, 20 equals 36 e to the negative 0.012 t. Take or divide both sides by 36, so e to the negative 0.012 t equals, let's see, I believe that's 5/9. Take the natural log of both sides. And then finally, divide both sides by negative 0.012. And this equals approximately 50. Now we do have to be careful. Is that 50 years or whatever? We have to remember we were talking minutes. So it is 50 minutes. And realize that this is a way to help determine like times of death and stuff like that. So if you're interested in the forensic sciences, then this is a formula that you will probably become very, very, very familiar with. And finally, we end with logistic models. And if you understand one concept of this, it's going to make your life a whole lot easier. And that is this. First of all, we have this model. That'll be 270 over 1 plus 32.75 e to the negative 0.192t. Now what's important to realize is this top number here, this is the limiting factor, okay, or the limiting size. So that means I can look at this and say I know the absolute maximum is going to be 270. It's not going to reach anything more, okay? But here we're asking specifically, what will the population be in 30 years? Well, that's t. So all we have to do is find p of 30. And it's nothing more than just making sure you put this into the calculator absolutely right. And so I'm not going to do anything more than just rewrite the fact that t is 30, and we have 270 up here. And so this will become approximately 245. 245 what? That's it, 245 species or individuals, or I'm not sure exactly how to label this, but realize that the absolute most we could have is 270. So 245, we're getting up there to about the maximum. Now with that in mind, realizing that we have limiting factors, number 11, we have a new logistic growth model, and it says what's the limiting size of butterflies? Well, according to the logistic function, since 680 is the numerator, that is the limiting size. So there will never be more than 680 butterflies. And finally, question number 12. Luckily asks what's the limiting size. So the limiting size is the numerator, or 25,000. 25,000 what? The number of people. So that would be 25,000 people would be the most that would be infected a certain number of weeks afterwards. So there we have it. Three main different types of problems, but all have their own meaning and purpose in different situations.